Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So using the three moment equations in finding internal moments and then deflections and slopes. Remember that the three moment equations, the equation itself has no slope involved in it, just the internal moments. So the derivation of the three moment equation is based on the area moment theorems. Therefore, we can find the deflections as well as the slopes after we determine the internal moments. So compute for the reactions, and by principle we can solve for the internal moments, and then we apply the area moment theorems. We draw the area moment diagrams, moment by parts, to determine the slopes. But before that, we cannot compute directly the slopes, just the deviations. And from there, we can compute the slopes. So many students have asked if the three moment equation can be used in finding the slopes and deflections, and the answer is yes. But you have to be flexible because the derivation is based on area moment theorems. So for this problem, you may solve this in advance for those who have an idea on how to use the three moment equations in finding the internal moments or internal moment reactions at the selected points on the beam, then compute what is or what are required in this problem. So for the beam loaded as shown, use the three moment equations in finding the internal moments at points B, C, and D, because the moment at A is 0, it is an external support and it is the end support also, so roller support, so that's why it's 0. At D it is fixed, so there is moment there. The three moment equation is, if you can recall, so for instance in span ABC with constant EI is MA times LAB plus 2 times MB quantity LAB plus LBC plus M sub C times LBC plus 6A1A over I over L1 for span AB plus 6A2B over LBC, or over LAB for L1, LBC for L2 equals 6CI times HA over LAB plus H sub C over LBC. So the middle point is B. So for BCD, you just replace A by B, B by C, and C by D, so on and so forth. So this is 0 plus 2 times MB, LAB is 5, LBC is 6, plus M sub C times 6. The value of 6A1A over LAB for this uniform load on span AB is WL cube over 4. So 25 times 5 cube over 4. While the value of 6A2B over LBC for span BC is P, which is 35, B, which is 4, all over L, which is 6, quantity L square, 6 square minus B square, which is 4 square. So this is equal to 35 times 4 over 6, quantity 6 square minus 4 square, equals 6EI. HA is 0 because the supports are unyielding. So if we imagine a horizontal line through B, it crosses A, it also crosses C. Or in other words, the horizontal line through B crosses A and B, so there's no HA and H sub C. So that's why we just equate this to 0. So simplifying, 11 times 2, 22 MB plus 6 MC equals negative 14,975 over 12. Call that equation 1. Then we apply three moment equation on BCD, and remember that the support should be uh, simple. So this D here by principle for three moment equation is modified into an internal hinge. Then we have an external hinge D prime with, so that the moment at D prime is 0 and the distance between D and D prime would be very small or almost 0. So MB times 6 plus 2 times MC, quantity 6 plus 8 plus MD times 8. The value of 6A1A over L1 for BC is PA over L, quantity L square minus A square, where P is 35, A is 2, and L is 6. So plus 35 times 2 over 6, quantity 6 square minus 2 square. Then the value of 6A2B over L2 for span CD is 7 over 60. So the centroid is closer to that. So 7 over 60. The other one is 8 over 60. So that's for the farther distance. So 7 over 60 WL cube. 7 over 60 times 45 times 8 cube. So equals 0. So of course, for those who can recall these values, then you can answer this. But for those who have forgotten the value of 6A1A over L1, 6A2B over L2, you need to review three moment equations, which is also derived in my playlist. Simplifying, 6MB plus 28MC plus 8MD equals negative 9184 over 3. Call that equation 2. Then finally, we apply three moment equation on span CDD prime. So we have MC times 8 plus 2 times MD, quantity 8 plus 0 plus 0 because moment at D prime is 0, equals plus 6A1A over L1. So 8 over 60, 8 over 6 WL cube. So 8 over 60, 45 times 8 cube. Then 6A2B over L2 for span DD prime is 0. There's no load there. Equals 0 because the horizontal line through the middle point D crosses C and D. Same is true with the horizontal line through C. It crosses B and it crosses D. That's why we equate this to 0 for the second part. Simplifying, 8MC plus 16MD equals negative 3072. Call that equation 3. So the allowed calculator is capable of solving 4 simultaneous equations. There are only 3 simultaneous equations here. So using that calculator, MB equals negative 42.272 kilonewton meter. M sub C is equal to negative 52.987 kilonewton meter. And M sub D is equal to negative 165.106 kilonewton meter. We then apply the moments and the direction here, and MB negative, so it is clockwise, MBA counterclockwise here. So as shown, call that AY, shear just to the left, OB, shear just to the right of B. Assume those directions. So this is MB 42.272 just to the right, counterclockwise. At C also 52.987 clockwise here. So shear just to the left, shear just to the right of C. Then this is the moment at C and the direction. So since we want to shorten the solution, I'll just use portion BC here. So I need to solve shear at B just to the right by considering BC and summing up moment about C. So shear BR times 6 plus this moment at C, which is 52.987, equals this moment at B, which is 42.272, plus 35 times 4. Again, share B right times 6 plus 52.987 equals 42.272 plus 35 times 4. So that's it. Solving for shear just to the right of B, it is equal to 21.548 kilonewtons. So therefore, to solve for the slopes, we apply uh, area moment. So we draw moment diagram by parts for portion BC, and I choose C as the moment center. So 21.548 times 6, it should be like that. 21.548 times 6, the value here is 129.288 kilonewton meter. Then the moment at B, which is negative 42.272, so we have 42.272 negative, and the moment of this load 35 times 4, so 140, but it is negative because we make C the moment center. So if you check 129.288 minus 42.272 minus 140, it should be negative 52.987 more or less. So I then compute EI, deviation of point C relative to the tangent at B. And from area moment theorems, it's just the moment of these areas with respect to C. So it is equal to 1 half area of this triangle, 1 half 6 times 129.288, moment arm is 2 from C. Then plus 6 times negative 42.272 times 3. Then moment of this area plus 1 half of 4 times negative 140. Moment arm is 1/3 of 4 or 4/3. Solving for deviation of C relative to B, it is equal to negative 358.501 over EI. Negative means that that point C is below the reference tangent at B. So the reference tangent at B should be above C because point C is below that reference tangent as shown in the figure. And this is deviation of C relative to B. So physically the slope at B, because it is up to the right, the angle here is above the x-axis, and the rotation from the positive x-axis is counterclockwise. Remember from trigonometry, rotation that is counterclockwise is positive. So this slope is positive. So that's theta B. Tangent theta B, remember, is equal to theta B itself because theta B is small. It is just opposite over adjacent. Tangent of theta B is theta B itself, and it is expected positive, so 358.501 divided by 6. Opposite divided by 6. So again, the reason why the value of deviation of C relative to B, which is the opposite of this right triangle, is treated positive because we anticipated that the slope at B is positive, and tangent of theta B is equal to theta B itself. So you have to, if you do not know that, you have to review the preliminary ideas on deflections in beams. So therefore, theta B is equal to 59.750 over EI. The direct way of computing theta B is to use slope deflection equation. So I will solve this problem using slope deflection equations also to verify that this answer is correct. Likewise, EI deviation of point B relative to the tangent at C, we'll just use the same area, same figure here, except that the moment arm would be from B. So if this is 2, this is changed to 4. If this is 3, this remains 3 because 6 minus 3 is still 3. And this is now 6 minus 4/3. So EI division of B relative to C equals 1 half of 6 times 129.288 times 4 plus 6 times negative 42.272 times 3, then plus 1 half of 4 times negative 140 times quantity 6 minus 4/3. So solving for deviation of B relative to C, it is equal to negative 516.107 over EI. The negative sign indicates that point B again is below the reference tangent. So the reference tangent at C should be above B because B is below that reference tangent as shown. And this is theta C. If this is also theta C, so from the positive x-axis to the tangent at C, the rotation is clockwise, and clockwise rotation is negative. Therefore, the slope at C is negative. It is negative 516.107 divided by 6 EI. So tangent of theta C or theta C is equal to opposite over adjacent. Tangent theta C is equal to theta C itself. So negative 516.107 over 6 EI. We anticipated that theta C is negative. Therefore, theta C is equal to negative 86.018 over EI. Then for the deflection under the 35 kilonewton load, so I just draw the deflected shape, and I'll assume that this is the deflected shape, so that a horizontal line through this means that points B and C will be above that horizontal line, and I'll call that point 1. So I'll call that point 1. This is now point 1, and remember that HB equals H sub C. So this is HB above the horizontal line through this elastic curve, which is point 1. HB equals H sub C because this is a horizontal line. And the assumption here is because B and C are above that horizontal line, they should be positive. If the result after using the three-moment equation is positive, so that's correct. So the deflection at 1 is below the horizontal line of the beam or the neutral axis of the beam, so it is a negative deflection. However, if it is negative, so meaning to say B and C will be below the point on the elastic curve, and the elastic curve should be above because the horizontal line would be above B and C, so B and C will be below. So that's it, as simple as that. So if HB, HC, or HB is positive, so this is correct. So delta 1 would be negative or downward. But if HB is negative, so it means the elastic curve is above the horizontal line of the beam, and the deflection at 1 is positive. So what is the moment at 1? So the moment at 1 is simply we sum up moment, or we take moment about 1. So it is shear at B just to the right times 2. Then plus the moment at B, which is negative 42.272, which is solved in the preceding slide. So recall the shear at B just to the right, 21.548 kilonewtons. Moment at B, negative 42.272 kilonewton meter. Moment at C, which is negative 52.987 kilonewton meter. So before we can write three-moment equation on span B1C, we need the moment at 1, which is simply shear at B just to the right. So it is clockwise positive. Remember the sign convention. Times 2, then minus this moment, which is 42.272. So moment at 1 is 21.548 times 2, then plus supposedly this moment, because this is counterclockwise, about 1, so it is minus negative 42.272. So moment at 1 is 0.824 kilonewton meter. Then we apply three-moment equation on B1C. So moment at B, negative 42.272 times span B1, which is 2, then 1C, which is 4. So negative 42.272 times 2 plus 2 times 0.824 times 2 plus 4 plus negative 52.987 moment at C times 4 span 1C. Then 6A1A over L1, there's no load between B and 1, so 0. 6A2B over L2, there's no load between 1 and C, so it is also 0. Then equals 6EI HB over L1, which is 2, plus 8 sub C, but 8 sub C is just HB because this is horizontal line, so B and C are unyielding support, so HB equals H sub C. So HB over 4. Solving for HB is equal to negative. So because it is negative, it contradicts with this assumption here. So meaning to say the elastic curve at 1 is above the horizontal axis of the beam. So it's here. That's why B and C are below that point, that horizontal line through the elastic curve. So it means that the elastic curve really lies above the horizontal axis of the beam. So the deflection at 1 is positive. So we just make this positive, and that is delta 1 automatic. So delta 1 is 63.69 over EI. So that's it for this video. I hope that you were able to follow and understand the explanations.